Hello, so welcome back to another video. Today we will be continuing on our derivation for the energy Navier-Stokes equations. And in my last video, I derived this equation that we see right now, which essentially states the internal energy plus the kinetic energy shown on the left-hand side, the time derivative of that, equaling to the change in energy inside of the control volume, which are a sum of different changes in energy, different aspects, such as the transport, internal energy, and kinetic energy. We have the heat transfer, then we have the compressive, normal, and shear stresses. We also have body forces and some an external energy expression. So now we will be using some math techniques to kind of make this equation look nicer. So here, to continue on with our work, we can say that on the left hand side, and we'll call this LHS, left hand side, we can say that partial t of rho e plus the velocity magnitude squared over 2 equals out to be the following. Here we are using product rule. Partial rho, partial t, plus rho, partial e, plus velocity magnitude squared over 2, partial t. And we'll say that this is product rule. Similarly, on the right hand side of the equation, right hand side, looking at the dE term, dE dot term, we can say that partial x rho e plus velocity magnitude squared g down here, we can move that a little bit up here, velocity magnitude squared over 2 u equals out to be e plus velocity magnitude squared over 2 partial rho u partial x plus rho u partial x e plus velocity magnitude squared over 2. And we can do the same thing for the y and z term. Lastly, for the z term, two partial rho w partial z plus rho w partial z e plus velocity magnitude squared over 2. And boom, we have our 3 terms. So now we can reorganize the equation that we have above, and that will give us the following. Reorganizing you get the following. E plus velocity magnitude squared over 2 partial rho partial t plus partial rho u partial x plus partial rho v partial y plus partial rho w partial z plus rho partial e partial t plus u partial e partial x plus v partial e partial y plus w partial e partial z plus the velocity magnitude squared over 2 term, rho times partial velocity magnitude squared over 2 partial t plus u partial velocity magnitude squared over 2 partial x v partial velocity magnitude squared over 2 then the w component. This term, this will equal out to be the following. Partial x, this is our heat term, lambda partial t partial x plus partial y, lambda partial t partial y plus partial z, lambda partial t partial z minus p partial u partial x plus p partial v partial y plus p partial w partial z minus u partial p partial x plus v partial p partial y plus w partial p partial z plus u partial sigma xx x partial tau yx partial y plus partial tau zx partial z plus v partial tau xy partial x partial sigma yy partial y plus partial tau zy partial z plus the w partial tau x z partial x plus partial tau yz partial y plus partial sigma zz partial z plus sigma xx partial u partial x plus tau yx partial u partial y plus tau zx partial u partial z plus tau xy partial v partial x plus sigma y partial v partial y plus tau zy partial v partial z plus tau x z w partial x w partial y plus sigma z partial w partial z and plus our external energy or plus our body forces plus our external energy terms. And in case this isn't obvious, this term here is derived using product rule. And this term here is derived using product rule as well. That's where these extra terms jump in. So I would like to note that in the continuity equation, partial p, partial t, or partial rho, partial t, plus partial rho u, partial x, plus partial rho v, partial y, plus partial rho w, partial z equals out to be 0. So if we go back up to this term, we have this following here: partial rho partial t plus partial rho u partial x plus partial rho v partial y plus partial rho w partial z. So we can cross that term out because of the continuity equation. First term on left-hand side goes to 0. Also, for a Newtonian fluid, tau ij equals mu partial vi partial xj plus partial vj partial xi. And for 3D flows, we can use Stokes' hypothesis. We can use Stokes' hypothesis. This will be for 3D flow, three-dimensional. Sigma ij equals 2 mu partial vi partial xj minus 2/3 mu partial u partial x plus partial v partial y plus partial w partial z. And again, I won't be going over the details of Stokes' hypothesis. I will only be applying the hypothesis for this video. However, if you would like more information on Stokes' hypothesis, I will leave a link down in the description. So with tau ij and sigma ij, we can write the following terms. Therefore, the following terms we can write are sigma xx equals 2 mu partial u partial x minus 2/3 mu partial u partial x plus partial v partial y plus partial w partial z. For sigma yy, partial v partial y minus 2/3 mu partial u partial x plus partial v partial y plus partial w partial z. And lastly, we have sigma zz 2 mu partial w partial z minus 2/3 mu partial u partial x plus partial v partial y plus partial w partial z. Now we have our tau xy and our tau ij terms. Tau xy equals out to be tau yx, which equals mu partial v partial x plus partial u partial y. Tau xz equals out to be tau cx, which equals out to be mu partial u partial z plus partial w partial x. We have tau yz equals out to be tau zy, which equals out to be mu partial v partial z plus partial w partial y. And when we focus on the following stress terms, we will be focusing on these terms here where I'm highlighting. So the terms we'll be focusing on is circled in green, like that. So when we focus on these terms, I think it'll be better if I did this. Grab it. So focusing on these terms, let's see over here. So focusing on these terms here, let's do that. So we'll call this section 2.1. We'll call this equation 2.1. We'll call this 2.2, call this 2.3. So looking at 2.1, we have u partial sigma xx partial x plus partial tau yx partial y plus partial tau zx partial z. This equals out to be u partial x to mu partial u partial x minus 2/3 mu partial u partial x plus partial v partial y plus partial w partial z plus partial y mu times partial v partial x plus partial u partial y plus partial z mu partial u partial z plus partial w partial x. This will equal out to be u 2 mu partial squared u partial x squared minus 2/3 mu partial x partial u partial x plus partial v partial y plus partial w partial z plus mu partial squared v partial x partial y plus mu partial squared u partial z squared plus partial squared w partial x partial z. (2.2). Now, this is our equation for 2.1. Now for 2.2, we have the following. V partial tau x y partial x plus partial sigma yy partial y plus partial tau zy partial z equals out to be v times partial x mu partial v partial x plus partial u partial y plus partial y 2 mu partial v partial y minus 2/3 mu partial u partial x plus partial v partial y plus partial w partial z plus partial z times mu partial v partial z plus partial w partial y. This will equal out to be the following. V times mu partial squared v partial x squared plus mu partial squared u partial x partial y plus 2 mu partial squared v partial y squared minus 2/3 mu partial y partial u partial x plus partial v partial y plus partial w partial z plus mu partial squared v partial z squared plus mu partial squared w partial y partial z. And we'll end 2.2 with this expression. And lastly, we have 2.3. Of w partial tau x z partial x plus partial tau yz partial y plus partial sigma zz partial z equals out to be w partial x mu partial w partial x plus partial u partial z plus partial y mu partial v partial z plus partial w partial y plus partial z 2 mu partial w partial z minus 2/3 mu partial u partial x plus partial v partial y plus partial w partial z. This will equal out to be w mu partial squared w partial x squared plus mu partial squared u partial x partial z plus mu partial squared v partial y partial z plus mu partial squared w partial y squared plus 2 mu partial squared w over partial z squared minus 2/3 mu partial z partial u partial x plus partial v partial y plus partial w partial z. That is the end of 2.3. And note that 2 partial squared vi over partial xj squared equals, not to be partial squared, vi partial xj squared. We'll have additional term partial xj partial vi partial xj. We'll use this to help us make this equation, break down this equation further. So you can say that rearranging 2.1 plus 2.2 plus 2.3, we get the following. We get mu u partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared plus mu v partial squared v partial x squared plus partial squared v partial y squared plus partial squared v partial z squared plus uw partial squared w partial x plus partial squared w partial y squared plus partial squared w partial z squared plus 2/3 uu partial x sorry, no 2/3 term here. Partial u partial x plus partial v partial y plus partial w partial z plus mu v partial y u partial x plus partial v partial y plus partial w partial z plus mu w partial z partial u partial x plus partial v partial y plus partial w partial z. We'll have this term be subtracted by the 2/3 portion of the equation, which is the exact same terms as the ones I've just written. So we can actually lasso this. move this over here. Change some of these terms to subtract minus 2/3 and change the coefficient 2/3 and 2/3. So therefore, in our original equation, we have the left-hand side, and we'll just break it down into left-hand side equals out to be E plus velocity magnitude squared over 2 times partial rho partial t plus partial rho u partial x plus partial rho v partial y plus partial rho w partial z plus rho partial e partial t plus u partial e partial x plus v partial e partial y plus w partial e partial z plus rho times partial velocity magnitude squared over 2 partial t plus u partial velocity magnitude squared over 2 partial x plus v partial velocity magnitude squared over 2 partial y plus w partial velocity magnitude squared over 2 partial z. We can say that the right-hand side equals out to be the following. We have our heat transfer term, partial x, lambda partial t partial x, plus partial y, lambda partial t partial y, plus partial z, lambda partial t partial z, minus the pressure terms, P partial U partial X plus P partial V partial Y plus P partial W partial Z minus U partial P partial X plus V partial P partial Y plus W partial P partial Z plus the terms that we have created, that we have derived right here. So we can just lasso this. we can take this term, move it up. And these will be 1/3. Because up here, since these terms are the same, this is 1 minus 2/3, which will give us 1/3. So that's why we have our 1/3 here. Perfect. So now we can write our other terms. X partial u partial x plus tau yx partial u partial y plus tau zx partial u partial z plus tau xz partial w partial x plus tau yz partial w partial y plus sigma zz partial w partial z plus our body forces k dot v plus our external energy rho dot q dot s, or rho times q dot s. And we will call this equation 3.1. So before we finish off today, let me recall, actually first, let me erase this. First, let's recall the Navier-Stokes momentum equations. In order to simplify, (3.1) recall the Navier-Stokes momentum equations. Say that x momentum is rho partial u partial t plus u partial x plus v partial u partial y plus W partial U partial Z equals Kx minus partial P partial X plus mu partial squared U partial X squared partial squared U partial Y squared plus partial squared U partial Z squared plus 1/3 partial X partial U partial X plus partial V partial Y plus partial W partial Z. For the Y momentum, we have rho partial V partial T Lastly, we have the Z momentum. And to simplify, first we will be using the X, Y, and Z momentum equations. We're going to multiply U, V, W to X momentum, Y momentum, and Z momentum, respectively. Then add equations together. So we would be adding the left-hand side together, and then we'll also be adding the right-hand side together after we multiply U, V, and W to X momentum, Y momentum, and the Z momentum equations, respectively. But for now, that is all the time that we have for today. And I will have these notes online for you for free. They'll be down in the link below. If you have any questions or comments, please shoot them down below. And I'll also have Stokes hypothesis down at the link below if you would like to learn more about that. And plan on having the third part of the energy equation derivation video for you as soon as possible. And I would like to thank you so much for your time today, and please have a great rest of your day.